Alright, welcome to the Science Hutch. The purpose of this video is to help walk you through using some basic math skills with Ohm's law and Joule's law, and maybe even combining them. We're also going to see how to linearize Ohm's law and what that means. So this is my little buddy Maggie. She's going to go ahead and go on the floor. And let's start cracking out some physics. Now, if you're in my class, you're going to need your packet that looks like this. Would have my computer screen. I'll show it here on the screen here. And you're going to scroll all the way to page number 10 to join me and start mathing this stuff. So let's get there. Page 10. Boop. Now, just for today's lesson, page 10 starts us off on working with electric charge and Coulomb's law. We're only going to need to review numbers 1 through 4 here, so we're going to do that. And then, just as a note to my students, when you're doing your work here, I've given you all the answers to all of these practice questions. Your job is to explain the answers in these open spaces. So I'll kind of walk you through that a little bit, give you a couple of examples. So here we can see numbers 1, 2, 3, 4. I've already circled the answers in green. I just looked them up on page 15 for this question set. And let's explain number 1, just to give you an idea of how to do that. When there's no math involved, you have to use some English words, and when there's math involved, you can just show your equation, substitutions, and then answers with correct units. So no math involved in this. Number 1 says a unit of electrical energy is the, and then we are selecting the joule. And so you could just say, well, okay, it'd be a little oversimple to say that the joule is the unit for electrical energy. So let's say something extra. Maybe the joule is not any unit for electrical energy. It's the SI, the System International unit for all types, there we go, of energy. And you could even say something like the joule is named in honor of James Joule. So there's an example of a couple things that you could write just to show, you want to prove to me that you didn't just circle answers, that you actually put some thought into this, and that you have something to contribute in addition to just the answer. Number 2, the coulomb is the unit of electrical charge. The coulomb is abbreviated capital C, so you could say something like that. You could also tell me who the coulomb is named after. And then charge, we're going to need to know this in a little bit. Charge is abbreviated, that quantity charge is abbreviated with a Q. Now you can use a capital Q or you can use a lowercase q. That's kind of up to you and your choices for my class. Electrical potential of 1 joule per coulomb is equal to 1 volt. Now, how do we explain this? We can do this with literary equations. Literary meaning letters, and so we use an equation that just is letters. Well, the definition of a volt is what we have here, electrical potential of 1 joule per 1 coulomb. And so voltage can be seen, here in purple V, voltage can be seen as energy per charge. And so I have a capital E there in orange for energy, and charge is my Q, as I just saw in question number 2. And so then if you put in the units for energy and charge, you'll be putting in and this is kind of leading us through what we've just done. So you'll be putting in parentheses, I'll put units, and outside of parentheses, you would put your quantities, like E is a quantity. It's not in parentheses. So in units, I would have the unit for energy, which we just saw is joule, named after James Joule, named after someone, so it's capitalized. And then that's going to be per over charge, and the unit for charge is a capital C, coulomb. And so we see electrical potential, also known as voltage, of 1 joule per divided by 1 coulomb is equal to the unit for voltage, which is a volt. Now be careful with this capital V. That capital V in parentheses is referring to volt, and then the V over here, not in parentheses, is referring to voltage, the quantity. Number 4, electrical power is measured in units called watts. And again, all forms of power are measured in the unit of watts. And there's a little joke you can say, it's very corny, but you can say watt is the unit for power, and the physicist would just answer yes. You're correct. All right, now, that's all we need to do in this question set, 1 through 4. And again, you're going to explain number 4 on your own. Let's go all the way to page number 16 in our packet. Page number 16. And now on here, we're going to do every question in this question set on electrical current, except for number 2. So you can skip number 2. Isn't that just wonderful? It's not going to relate directly to our test right now. It's a good question, but we don't need to know it right now. Now, again, number 1 is just reiterating the unit for all forms of power, not just electrical power. And then we've just talked about that. So let's take a look at numbers 3 and 4. I've circled them together in orange there because they're kind of a package deal. So number 3, which device can be used to convert mechanical energy into electrical energy? And so we need to know that mechanical is referring to motion. You can kind of link those in your mind with M for motion, M for mechanical. And here's this, let's take these 2 questions as a package deal. So then the second question says, the physical structure of an electric motor most closely resembles that of what? And the answer is an electric generator. And the physical structure is referring to how it's built and what it's made of. And so here's the idea. If a generator, and I've written this in green in number 3, if a generator converts motion into electrical energies, then a motor converts electrical back into motion energies. And so your electric cars are going to have electric motors in them, and they're going to take electrical energy from a battery, and they're going to convert it into motion in the car. But a generator, on the other hand, will take it will take your motion energy. You have to get something moving, usually maybe like a turbine or some pistons, and you're going to get those moving, and then it's going to convert that motion energy, we call it kinetic energy, into electrical energy for you. They're really just the opposite of each other. You know, one is going to have some kind of turning wheel, and you're going to either, and then you could use a battery to make the wheel turn, or you're going to have the turning wheel charge the battery. And so that's just the setup there. So the physical structure is very similar. It's just that one runs backwards when you look at the way the other one runs. So they're almost in a way like mechanical inverses of each other. And let's take a look at number 5 here. We're looking at another energy conversion tool that we humans have developed, and they're going to call it a dry cell. Now for us, dry cells, you can think of it as like these batteries. So like this D cell battery is a dry cell, so our double A's, triple A's, all of these cylindrical batteries are dry cells, meaning that the compounds inside, the chemicals inside are mostly dry, like a dry paste. And we're going to see a chemical reaction happen between those compounds in what you could call like the positive terminal and the negative terminal of the batteries. They're going to do a chemical reaction that will allow charge to flow from the battery, from the positive side to the negative side of the battery in one direction. So we say it's going to produce direct current, one direction. Number 6, let's go deeper into this idea that chemical energy can be converted into electrical energy by means of a zinc-carbon cell. Now zinc-carbon are 2 different elements, and one is going to be an electron giver, the other one's an electron receiver, and you'll learn more about that in chemistry. But here in physics, we're just interested in the fact that you're going to have a chemical reaction happening there between zinc and carbon, and it's going to create an electrical energy. It's going to actually produce a difference in energy from one point to another in a battery. Now I've labeled the other kinds of things there A, B, and C, but we're not going to take the time to go into those, or else the video will get quite long. Let's look at number 7. Electrical insulators are used to resist the flow of. So the best thing to say is that electrical insulators, they can hold charge, but they resist the flow of it. So charge can stick onto them, but it doesn't move around on them. And then conductors would be the opposite of that, where conductors are used to allow the flow of electric charge. Now, speaking of conductors, let's look at number 8. Number 8, it says, in a simple electric circuit, connecting wires are assumed to have a resistance of, and the answer is 0 ohms. Now, ohms is the unit for resistance. And in basic physics, we have to talk about wires like they're magic wires. So we have wires that have no resistance to them because it's pretty difficult to factor in the resistance of the wire in addition to the resistance that all the little resistors are giving us in the circuit. So use magic wire with no resistance. Here you're going to have a charging by conduction. You're going to have two charged objects. They're going to touch, so they're going to conduct. And we're going to see in number C, or letter C, that you have extra electrons on the ball on the right, and then you have extra protons on the ball on the left. And these electrons are going to move onto the protons to help neutralize the system. The opposites are going to attract there. And so that's going to be the correct direction that electrons would move. A would be showing the direction that maybe protons would move, and that's not what the question was asking. It was asking about the flow of electrons. B, you have less electrons here than you have here, and so you have less negative charge. And these are actually going to repel. And then in D, these are also going to repel, so you're not going to see electrical charge. Now they may kind of even out. So if you have if this is these 4 negatives in B are representing maybe a 4, maybe let's say a 4 coulomb charge here, then you might have a 2 coulomb charge here, and this would be negative, and this would be negative. And then after they touch, those will kind of even out, and so you'll have maybe a negative 3 coulomb charge on each of them. Total charge will be the same. Like overall, you had -6 when you started, and so you'll have -6 afterwards. But that's your little bit there. Now let's look at number 10.